Math 236. Well, this is our last lecture of this week. Today is Thursday, April 9th. So we are about to start a new section today, section 11.4. This is the last section that will be on our test, right? Which is 1 week from today. You got an email about that from me today, right? And speaking of tests, 11.4, we get 2 new tests, okay? And here are the abbreviations for them. Usually we'll do this one first because we use this one to prove this one, but we're going to do this one first because we're not going to prove anything today. Sadly, I know you're sad. We're going to save the proofs for next week, and we're going to dive into this guy first, okay? And I'll tell you what these abbreviations stand for here in just a sec. So, one thing for you to think about is, what are our go-to tests so far? For testing what, right? Testing series, whether a series converges or diverges, right? That's kind of our big question these days, and that's what our 2 new tests are for, right? 2 new tests for convergence. Ooh, this is a much better marker than that one, right? For convergence or divergence of series, right? Okay. What's our favorite right away to series? Some A sub k or A sub n. Your book uses n. I'll keep trying to use n. Sum A sub n, it doesn't matter, right? Okay, summing infinitely many things. Alrighty, so hopefully you thought about this, and now let's write down what these things are. Okay, now these tests are tests that apply. These are 2 new tests that apply for series with all positive terms. Okay? Our series have to have all positive terms. Now, some of the tests that you wrote down over here also needed positive terms, some didn't. Maybe you ought to think about which ones did or didn't. If we could ever do a lecture without a phone call, oh my. All right, I'll just let that pick up. So here we are. So what does LCT stand for? Okay, so LCT stands for the limit comparison test. And this limit comparison test, another reason why, since we're just going to do examples of utilizing the test today, is that test is one that gets used a lot more in problems, whereas the comparison test also gets used a lot more in problems, but oftentimes a lot more in the theory to prove other easier tests. Okay, so the CT stands for comparison test. Okay. Comparison test and our limit comparison test. These are our topics for today, okay? And proof of these things will be coming next time. All right, so what does the limit comparison test say? Well, like we just said, in fact, this is going to be a little bit more expanded version of the limit comparison test than is in your book. So we start with series. So this time we're going to have 2 series, some AN and some BN, right? We're going to have 2 series. So let AN and BN both be series. Like we just said, with positive terms. What does that mean? It means we're just adding up positive things, right? So, i.e., AN is positive for all n, and BN is positive for all n. Yeah? Okay? So that's the first kicker. If your terms aren't all positive, then you can't be using these tests, okay? All right, so let's see. So we're going to say that there's 3 pieces to the limit comparison test, okay? The first piece says if I look at the limit as n goes to infinity, okay? So now we're going to be taking some of these limits of an over bn, right? So that's a ratio of the elements of these series. And that limit exists, okay, and equals some number L. And that number L is a real number which is not 0. Okay, so this is what I was saying. You got to have your other go-to tests down because we're going to start getting a little bit tricky. So I take this limit. I see if that limit exists. L means it's a single finite real number, right? And then I check to make sure that number's not 0. Okay, well now remember, an was positive and bn was positive. So positive over positive, right? This limit is either going to be positive or 0, right? And so by saying L isn't 0, we're actually essentially saying L had to be a positive number, right? Okay? L is not 0, yeah? Okay, so if that is true, then what? Then these 2 series have the same behavior. What do I mean by behavior? Good, right? Whether they converge or diverge. They either both converge or they both diverge. Yeah? What does that mean? Well, that kind of means, how does this actually work in practice, right? So that kind of means that I've got these 2 series, right? And usually this guy is the one that I am given that I don't know its behavior, right? This is the given series, right? That we're trying to determine whether it converges or diverges. We don't know its behavior. We don't know its behavior. And this one, Bn, is one we introduce we know its behavior, so that if we look at this limit and then we get a number L, or we get a limit that is any number that's not 0, right? You shouldn't get anything negative or positive, right? You get a non-zero number, then you know that those 2 things have the same behavior, but you purposely picked this guy because you knew its behavior, right? Okay? And that will tell you the behavior of the harder series that you don't know the behavior of, right? Okay, so for a moment here, let's remember, what are our go-to tests so far? Okay, what do we know? What tests allow us to know the behavior of a series, right? So there's essentially really 4 of them. Yeah, did you come up with 4? Okay. The main ones that we think about, our first guy, our kick-out test, right? He's getting better, right? Is the good divergence test, okay? That's our first guy to think about, our divergence test. Then what was the next one? Good, geometric series. Right, we have a nice test for geometric series. Make sure you know what a geometric series is and what the test is for it, and all the other fun things we did. What is the next type of easy series to look for? Easy series? Good. P-series, right? We know the behavior, convergence or divergence of P-series, right? Okay. And finally, then what else? What was the last section? Good. Integral test. Okay, so these are our guys for the most, where we can get quicker results. Okay, so oftentimes P-series is the one that we do for this. Pick a BN. Okay, not always, but most of the time. You want to pick BN to be a series whose behavior you know. And then you got to cleverly choose it so that when you create this limit between the terms of the series you don't know and the terms of the series you do know, that you get a limit that's not zero. Now, what if you got a limit that was zero? Is all lost? Well, not if you do your homework, right? Because one of your homework problems, which is homework problem number 40, is really what we're calling the second part of the limit comparison test, okay? So what does that say? Well, that says if the limit as n goes to infinity of an over bn is equal to 0, right? That was one of our other options, right? This is positive. So, so we're either going to have a limit that's positive or a limit that's 0. We can think about what the other options be. But if that guy equals 0, well, then this piece tells you nothing, right? Is all hope lost? Well, the answer is no. If this limit was equal to 0 and I chose my BN such that it was a convergent series, so if that limit does equal 0 and your BN converged, then what do you think you're going to be able to say? Good. AN converges also. Okay, so if your BN diverged, then and you got the limit of 0, you're out of luck. You got to pick a different BN. Yeah? Okay? Okay. So what do you think the next piece is? Homework problem number 41. Yeah? Woohoo! Yay! That's the third part of the limit comparison test. Yeah? What do you have a guess? You have a guess what this is going to say? What do you think? What do you think? What's the other option for this limit? If the limit as n goes to infinity, an over bn, we got the option of it being 0, we got an option of it being any positive finite number. It's positive over positive, so what's the only other option? Grows unbounded, right? What if that limit goes off to infinity, right? Grows unbounded and positive. Well, are we out of luck? Well, the answer is no, right? What do you think? What do you think is going to be the parallel thing? If I take that limit and the limit ends up growing unbounded, going off to positive infinity, and it so happened that my what? My series I know the behavior of, the one I chose, does what? Good. Diverges, that was a good thought. Then what? Then my series I don't know the behavior of also diverges. Okay? So we're going to just try to get comfortable with the application of these tests and prove them next week. Some I'll prove, some you'll prove, right? Okay? These homework problems are the proofs. Okay, so does this make sense? Are we good? Are we ready to roll with this test and just see how to roll it out? So again, remember, when you're doing this test, limit comparison test, how do you let me know that that's what you're doing, right? You're like LCT, right? LCT, I'm doing the limit comparison test, yeah? Okay? And then you would have this limit calculation. You're going to have to say what your BN is. And remember, what is the limit calculation, right? The limit calculation is you're computing the limit as n goes to infinity. The numerator guy is the series that you're trying to figure out what the convergence or divergence is, and the denominator guy is the series that you picked that's oftentimes a p-series that you already know how it converges or diverges. And then you're basically just seeing what comes out of that limit, right? You're always hoping that it's some non-zero number that's finite because you're golden, right? If it's 0, you got to make sure you had a convergent series. If it goes off to infinity, you got to make sure you had a divergent series. Otherwise, towards you nothing. Yeah? Here we go. Maybe I will try to do the whole, slide this guy out, flip that screen this time, just so we keep that up there. Woohoo! Magic, right? Let's see. Yikes. Can I not? Well, maybe this wasn't a good idea. If I don't turn that screen back over before we end here, then it definitely wasn't a good idea, right? Okay, let's try a problem and make sure the video is running. Yay. Okay, let's look at example. This is exercise number, section 11.4, number 22, okay? All right, so here we have sum n equals 3 to infinity of n plus 2 over n plus 1 quantity cubed, okay? Again, this guy starts counting at n equals 3, doesn't matter, we don't care. As long as what's in here exists, right, at these values, right? So clearly n equals -1 is where you have trouble, but that's not in the game, yeah? So what are the ANs here? The ANs are n plus 2 over n plus 1 quantity cubed, right? That's what we're adding up. And, again, quick little checklist ought to go off in your head. Would the divergence test help you? No, that limit's going to go to 0, okay? Is this a geometric series? No. Is it a p-series? No. But it's kind of close, and that's what's going to tell us, well, p-series might be the thing that we want to do. It's going to help us figure out what p-series to pick for our limit comparison test. Would the integral test work? Yes. Do I want to do the integral test? Well, it's a little bit more work, right? I mean, you got to justify the hypotheses, right? The 3 hypotheses, and then you got to actually do the integration and all of that. So, so in a lot of cases, like the limit comparison test might be a little bit simpler here. So let's go with that. So you're gonna say, hey, I'm doing the limit comparison test, okay? And now we want to figure out how do we choose the big question is how do we choose our BN series? How do we choose it well? Right? That's the question. Because we just saw from our 3 possibilities, if you don't choose it well, you might end up with something that just doesn't get you anything. Okay, so how do you choose it well? You analyze your AN series, okay? For its most important behavior, right? For large N, that's kind of the deal, okay? So, so what is the deal? So if I think about this AN, right? So it's n plus, I'll just rewrite it again, n plus 2, oops, over n plus 1 quantity cubed, right? So if I think about what this is kind of similar to, right? So it's not equal to, but it's similar to. If I'm thinking about n being large, right? Then if I compare n and 2, right? Then the dominant term really is, if n is going off to infinity, the dominant term is n, right? Okay? So that's kind of the deal there. It's the largest power of n, right? It's the largest thing we've got going on there, right? In the numerator. Now what about in the denominator? Well, this is n plus 1 quantity cubed, right? Now you could think about cubing that out. Probably don't want to. But if you did, what would be the very first term in the expansion? Yeah, it would be an n cubed, right? And then the rest of the guys would have n squared and n and a constant. And so what's going to be the dominant large n term here? It's going to be n cubed, right? Okay, so this expression is kind of similar to n over n cubed for large n. Does that make sense? That's kind of what I'm using this notation for, okay? All right, but n over n cubed is easier algebraically, right, than this, yeah? Okay, what is n over n cubed? Yay, right, it's 1 over n squared. And this is our hint. This doesn't work always, right, but this is our hint as to what to pick Bn to be, okay? So pick Bn to be 1 over n squared, right? Okay. Now, before we go on, what can you tell me? If that's Bn, what do you know about the series 1 over n squared? This is a what kind of a series? P series. Very good. What is P? P is 2, right? Yeah. What do we care about for a P series? What's important about whether P is good, bigger than 1 or not bigger than 1, right? 2 is bigger than 1, right? This is how you're showing me you understand what a P series and what the results are as well. So when I'm looking at work, I'm looking for work that shows you know what all the requirements are. So it's a P series, P is 2, it's bigger than 1, right? And what does that mean for a P series? P series with P bigger than 1 converges. Yeah? Okay, so our guess is that this guy converges. That's our guess. Now you have to justify that guess. Let's see if the limit comparison test will allow us to justify it. Okay, so what do we, so we're going to pick Bn equal to 1 over n squared. And then for this problem, what are we going to do? We look at the limit as n goes to infinity of, let me make sure you can actually see the board. Did I? Yeah, you can. Okay, good. Whew. The limit as n goes to infinity of what, right? An over Bn. Again, it is not overkill to write that down in general first so that you don't forget as we keep developing more and more tests what you're doing and why you're doing it, right? It's one little extra stroke or a few little extra strokes that will save you lots of extra headaches later. So what are we doing? We're looking at the limit as n goes to infinity of an. What is an? Well, it's n plus 2 over n plus 1 quantity cubed, right? Divided by Bn. What was Bn? 1 over n squared. Ooh, fraction math, right? Okay. And so we'll do this one slightly slower. So this is the limit as n goes to infinity. What is that the same as? I've got that fraction, which is n plus 2 divided by n plus 1 quantity cubed, right? And then this guy flips up, so that's times the reciprocal, n squared over 1. Yes? Are we good? Okay, so let's keep going along with our nice limit calculation. So what do we have here? This is the limit, right? Got to keep the limit in front. N cubed plus 2n over n plus 1 quantity cubed. Yeah? How do we deal with this limit? How do we justify this limit? Well, it's an infinity over infinity indeterminate form, so you could do L'Hopital's rule 3 times if you like, correctly. But we're going to use the method that we've been using throughout, which is we're going to divide by the highest power of n in the denominator, because that idea also carries over into other scenarios as well. Several of the examples in your book also utilize that concept with exponential type functions, so make sure you take a look at some of those examples as well, right? And so let's keep going with this limit here. So what we're going to do, just like those limits that were on your quiz in sequences, we're going to divide the top and the bottom each by n cubed, right? Because that is the highest power of n in the denominator, because we've got this cube out here, right? So if we did expand this guy, it would be n cubed. Yes? Okay? But we're not going to expand it. You can if you want. We don't have to. That's one of the reasons I chose this one, just so that we can see how to deal with this without expanding. Okay. So divide everything by n cubed, right? Here we go. So I'm going to write it all in there so we see it. N cubed over n cubed plus 2n over n cubed, right? All divided by n plus 1 quantity cubed over n cubed. Yes? Okay. So this is the limit as n goes to infinity of, this is good, 1 plus that 2 over n squared. Very nice. All divided by, now what should we do with this? I don't want to have to cube that out, right? Fraction math, exponent math, right? Very little of the math is really calculus, right? Okay, so what do? That's the same as n plus 1 divided by n quantity cubed, right? Yes? True? Fantastic. And then we'll just come down over here and keep going, right? So this limit equals all of these things. One more time, the limit as n goes to infinity. What do we have there? Before we take any limits, let's get everything in our final form before we want to think about, let's rewrite that more simply, right? N plus 1 over n. How can I rewrite that more simply? Good. 1 plus 1 over n. Why is that more simple? It's more simple for us in the computation of this limit, right? Okay? To undo that common denominator, yeah? Okay? Fraction math. Alrighty, we are here, right? So now, what do we have? We've got a limit, right? And we have all of our limit laws, right? And so, this is the limit of a quotient, it's the quotient of the limits, right? The limit of a sum in the numerator is the sum of the limits, yeah? And in the denominator, I can bring the limit inside the power, right? The limit of a thing to a power is the limit of the thing raised to that power. All those limit laws are come into play here, yeah? And by doing this step, right, we turn all of these guys into finite things instead of infinite things when we're here, yeah? As n goes to infinity. So you tell me, limit as n goes to infinity of 1 is 1. Good. Limit as n goes to infinity of 2 over n squared is? Woohoo! We see this limit all the time now. We love this guy. 0, right? 0. Constant over something getting huge. Going to 0, right? Now what about the denominator? What do we got? Limit as n goes to infinity of 1 is? 1. Beautiful. Limit as n goes to infinity 1 over n. Constant over something getting huge. Going to 0. Therefore, we don't need limit anymore. We just indicated we were doing the limit. So what's left in the top? 1 plus 0. Right. The bottom is 1 plus 0 cubed. What do I get? 1. Right? 1 over 1 cubed is 1. Woohoo! Why is that a woohoo? What do I care about? What were we doing? Oh yeah, it's the limit comparison test. What do I need? Why am I computing this limit? Because what do I want this number to be? I want this number to be not 0, right? This is my L that I got out of here, and it's not 0. 1 is not 0, right? And if you don't tell me that, I don't know that you understand. We understand? We got it? Okay? So, because we got a limit that is not 0, what does the limit comparison test tell us? Yeah? They both have the same behavior. The BN series and the AN series have the same behavior. And what did you say the BN series did? It converged, right? You said it right here. So there was no question as to whether or not you knew it, right? Therefore, the limit comparison test says that the sum of AN also converges. Right? If you want to, since the sum 1 over n squared converges, right? If we just want to at least put that in there. Yeah? Make sense? Yeah, so cool. Okay, let's look at what happens. Be even cooler when you see why it all works. But let's look at what happens if we pick the wrong BN, right? So let's keep working with the same problem. So this was our big question here with the limit comparison test. How do you choose the BN series well, right? So the fact that we would even ask that question suggests that you can choose that series not well and then not get anything out of it, right? And so let's look at what happened, what would happen there. So the question now is, what if we choose the wrong BN? Okay. So suppose we didn't know anything about this particular problem, and we were just like, okay, so here now we're choosing the wrong BN. Okay, so if we had chosen, say, BN equals 1 over n cubed, for example, and been like, oh, hey, it's kind of like n cubed in the denominator, let's pick that. What would have happened? Then we would have had a limit as n goes to infinity of an over bn, right? That's what you do for a limit comparison test, right? Okay? And then it would have been our same thing. Limit as n goes to infinity of n plus 2 over n plus 1 quantity cubed. I shouldn't have erased, right? I could have just changed things. Oh well. 1 over n cubed plus 1 over n cubed. Yeah? Which would have been the limit as n goes to infinity of n plus 2 over n plus 1 quantity cubed times n cubed over 1, right? Maybe I should have just used a different color. Okay, well, we're moving along now. Which would have been what? I'll come down here. The limit as n goes to infinity of n to the 4th plus 2n cubed over n plus 1 cubed. Yeah? And if we did the exact same thing where we divide by the highest power in the numerator, in the denominator, then we would have had, we would divide each term, divide every term by n cubed, right? And then we'd have n to the 4th over n cubed, and that would give me n, right? Well, maybe I'll just write it so you see it. Plus 2n cubed over n cubed, plus our same guy, right? n plus 1 cubed over n cubed. Yeah? What would we be left with then? We'd have a limit as n goes to infinity of n to the 4th over n cubed is n. That guy is a 2. All divided by, we saw that this guy goes to that, right? 1 plus n plus 1 over n, quantity cubed, and then 1 plus 1 over n, right? So here we would be left with this limit, very similar, right? The whole process was totally similar. And this guy goes to 0. So what would we be left with? We'd be left with something where the denominator is going to 1 and the numerator is going where? Right? Growing without bound, right? Infinity plus 2 is just infinity, right? Growing without bound. So this thing would go to infinity, right? That would be that limit. Would we be able to conclude anything from the other part of the limit comparison test where this thing goes to infinity? That's part 3. Yeah, I knew I probably shouldn't have changed the board because it's going to take too much time to flip it back for you to see it. Anyway, you guys tell me, what was the other condition with part 3? You can only make a conclusion if your BN series did what? converged, right? What do we know about this guy? This is a P series. P equals 3. 3 is bigger than 1. And therefore, right, my BN series converges. Sorry, can't read that. My BN series would converge if I get a limit of infinity from my AN over BN and my BN converged. I just did a lot of fun calculus limit work for, nothing basically. What does that tell you? It tells you you picked the wrong BN, okay? But BN converges, so we know nothing. Part 3 of the limit comparison test does not apply. You picked the wrong BN. And that's sad, okay? Picked the wrong BN. Here's the reason not to have a home phone. I may just have to cancel the home phone. I don't think I'm going to make it through online semester with my home phone ringing all the time. Okay, anyway, that's what it tells you, right? Okay, it means you got to go pick another BN, okay? You picked the wrong one. So we picked that one. We picked 1 over that wrong BN. Let's pick another wrong BN just to kind of see what happens, right? So what if we had chosen another wrong BN, okay? What if instead of 1 over n cubed, we had just picked 1 over n because we were lazy and bored and we just didn't want to possibly deal with another exponent, right? Let's just pick 1 over n, okay? Well then, what would we say about this P series? This is a P series with P equals, good, 1 into the 1, right? This is what series? Yeah? Say it all together now, in perfect harmony. Very nice. P equals 1, the harmonic series, right? And what about that harmonic series? It does what? Diverges. Right? Harmonic series diverges, yes? Okay? So if we pick that guy, right, then what would happen? Now I can just erase, okay? So I can erase that, right? Then what would happen? If we set it up with this same problem and we just picked 1 over n because we didn't want to deal with exponents, right? Then what would we be left with? That would be n over 1 here. Then what? When I would multiply through there, I would have gotten an n squared and just a 2n, right? That would have been the same. Then I do the exact same thing, divide every term by the highest power of n in the denominator, right? And so I would have had an n squared over n cubed and a 2n over n cubed, yeah? Okay, and that piece would have been the same. And then we'd come down here, and what is n squared over n cubed? Well, it is 1 over n, right? And what is 2n over n cubed? That's 2 over n squared, right? Denominator's all the same, so the denominator still goes to 1. Yeah? I think you're getting it here. The denominator goes to 1. 1 over n as n goes to infinity goes to? Good, 0. 2 over n squared as n goes to infinity goes to? 0. So what do I get in the numerator? 0 plus 0 over 1, right? Because 1 plus 0, right? Yeah? The denominator's 1 to 1 plus 0 cubed, which equals 0. Yeah? What happens if you get 0 out of the limit comparison test? You can't make a conclusion unless what? Unless your test series converged, right? This is case 2 of the limit comparison test is when you get a 0 as your limit. But what happened for RBN? RBN diverged. So what do we know? We know nothing again. In this case, part 2 of the limit comparison test does not apply. We got a limit of 0, but our comparison, the test that we had, RBN diverged. So the limit comparison test tells us nothing here. And what except for we picked the wrong BN again, okay? So you see, trying to analyze ahead of time is pretty important. Making sure you come up with the right series, be it a P series or possibly a geometric series, where you know the convergence, divergence behavior, and you have made some analysis of this guy so you can figure out what might be the right one, right? Our original one, Bn is 1 over n squared, was a right one. So I want to be a little bit careful. Is there a the right one? That's our next question, right? We just saw there are wrong ones, right? We just saw 2 wrong ones. So it's certainly possible to pick wrong ones. The next question is it possible to pick, well, maybe I will leave that up so I don't have to rewrite everything. Woohoo! Is it possible to pick, are there more than one? That's our next question. Is there more than one? What English class, right? Is there more than one right BN? Can multiple BNs work? Okay. And the answer is yes. Okay, but let's see. Let's do a new one. Okay, so let's this time pick Bn to be 1, and this will be the last time we do this problem, right? Okay, so we've been doing this one problem for a long time, but just trying for you to see what all the various things you may run into when you start trying to do them on your own, right? Okay, whether you pick the right Bn, the wrong Bn, or a different Bn that might have been easier or harder than the other one, but still giving you a good result. So here we go. What if we chose Bn to be 1 over n to the 3/2 this time? Okay, so 1 over the square root of n cubed. Yeah. Then this is a P series with P equal to what? Good, 3/2, right? 3/2 is good, bigger than 1. Therefore, what does Bn do? The series for Bn? Good, it converges, right? That's the P series result, yes? Good. So what would happen, here we go, I'm just going to keep rolling with this guy. The nice thing is you can stop the video, right, and write notes at whatever rate you want. And so we're going to divide this time An by Bn. This time we're going to use this Bn, right? When we do that, we'll come up here with a 3/2 power, yeah? This time, oh no, you guys are like wait, what's happening? We're going to multiply fractions. We're going to multiply n's with fractional powers. So if I do n times n to the 3/2, how many n's do I have, right? N to the 1. 1 is the same as 2/2. Rules of exponents. 2/2 plus 3/2 is good 5/2. Gotta know your rules of exponents, guys. So n times n to the 3/2 is n to the 5/2, and then I'll have 2n to the 3/2 sitting there. Yes? Okay. Same thing still happens with the denominator, right? We're getting the sense of this. So what do? We divide each term by n cubed, right? The highest power in the denominator. And so what will we have now? N to the 5/2 divided by n cubed to n to the 3/2, right? Divided by n cubed. This guy we know who he is. All right, now we'll just erase all of this. And so what do we get? This time I'll just continue in green here. So what do we have? We have the limit as n goes to infinity. So n to the 5/2 over n cubed. Woohoo! Oh man, this is getting crazy, right? N cubed is n to what? How many halves? Good. 6/2, right? 5/2 up here, 6/2 down there. What do I have left? 1 over n to the 1/2. Yes, 1/2 left down here. If I have n to the 5/2 up here and n to the 6/2 down here. Yes? Okay. What about this next guy, right? Okay, I've got 2 times, so I'll have my 2 there. And then I've got n to the 3/2 up here and 6/2 down here. What do I have left? Good. 3/2 down here, right? Yes? Good. You guys with me? And then that will all be divided by, again, what's our favorite way to rewrite that? It's 1 plus 1 over n cubed, right? That's our denominator, right? Once we do both steps at once. N plus 1 over n quantity cubed, and then n over n is 1 plus 1 over n, right? Here we are. What happens with this limit? Okay, we've done this denominator plenty of times. Where does 1 over n go? Goes to 0, right? As n goes to infinity, where does 1 over n to the 1/2 go? That's 1 over the square root of n, right? What's the range of square root of n? Off to infinity, right? 1 over something getting huge is going where? To 0, right? 2 over n to the 3/2. What's happening to n to the 3/2 as n grows large without bound? Denominator here is growing large without bound. Constant over something growing large without bound goes to 0, yeah? What do we get? This limit goes to 0 plus 0 over 1 plus 0 cubed, right? Yeah, that's what we got. The limit as n goes to infinity of 1 is 1. So what is that? 0 over 1, which is 0. Yay, right? Yeah, good. Okay. We got 0 out of the limit. What case is that of the limit comparison test? What we're calling case 2, right, of the limit comparison test. The limit was 0. You have one more thing to make sure of before you can quote any type of result, right? When we're in that case, when we get 0, what had to be true about our BN series? And our BN series, which was 1 over n to the 3/2, converged, right? Because it was the P series that was convergent. And so the limit comparison theorem, part 2, then says that our AN series converges. Make sense? So here's an example where we could have picked an entirely different BN than our original 1 over n squared and gotten the limit comparison test to work as well. Just a different case of it. Does that make sense? Okay? So think about that. We can make that test work. There's generally one nicest version that makes, one nicest BN that makes the computations work out as simply as possible. Yeah? Do another example? Okay, here we go. Let's see. I'm going to write this one up there, and I'm going to have you think about what BN ought to be while I erase the rest of the board. Okay? So here we go. Number 21. Which is the sum n equals 1 to infinity of the square root of 1 plus n over 2 plus n. What should you do? Quick thoughts. Divergence test, no. Not going to work. Geometric series, nope. P series, nope. Integral test, don't want to integrate that. Okay, so, yeah. Limit comparison test, right? Okay, that's where we are. Yeah? Okay, so, limit comparison test. Okay? gonna pick Bn to be what? That's the question. So what's our An? Our An is the square root of 1 plus n over 2 plus n. Yeah? An idea? Have any ideas? What should we do? An is approximately, right? It's approximately, maybe I'll just rewrite the analyze An, right? That's what we're try to analyze An. So the square root of 1 plus n over 2 plus n is kind of like the square root of n over n. Yeah, for n really large. Yeah? Okay. This is simple algebra. What is the square root of n over n? 1 over the square root of n. Yeah? N is always positive, remember? And so this is 1 over n to the 1/2. This is a p series, right? P is 1/2. 1/2 is less than 1. Therefore, this guy diverges, right? So this is a divergent p series. So that makes you think, okay, if I pick Bn to be 1 over n to the 1/2, I'm expecting this to be also a divergent series. So that if I add these guys up, right, the square root of 2 over 3 plus the square root of 3 over 4, when n is 2, right, plus when n is 3, the square root of 4, 2 over 5, right? If I add all that up and keep on going forever, I expect that to grow unbounded. Yeah? Okay, let's see. Limit comparison test. What do I do with the limit comparison test? I take a limit of comparing two series, right? Which is different than the comparison test, which is coming up here in just a sec. This is our last example. Then we're going to talk about what the comparison test is. So I compare two series with a limit. What is my limit? My limit is n gets large, right? And what am I comparing? An over Bn, right? An is the series I don't know anything about. Bn is the guy I picked. Limit as n goes to infinity. What is An for us? Square root of 1 plus n over 2 plus n. What is Bn? 1 over the square root of n, right? Yeah? Okay. What do we do? Well, let's make it look nicer. Fraction over fraction. You're going to have to get used to fraction over fraction. There's going to be so many limits of fractions over fractions for the rest of the semester. Okay? So, what is this limit written more nicely? It's the square root, right, of 1 plus n over 2 plus n, right? Times, right, square root of n over 1. Yes? Good? Okay. Well, now what do we do? Square root times the square root, right? You want to do some correct algebra. So we have on top the square root of 1 plus n times n, right? I'll just write it there like that so you see it. Yes, the square root of a times the square root of b is the square root of a times b. Both a and b are positive. Right over 2 plus n. Yes? Good. Okay, well, we kind of have the same idea that we want to work with, but the square root is super annoying, okay? And so, let's see, what is going to be our tactic? So we've got the limit as n goes to infinity. We've got this square root of, oh, we really kind of want to multiply that out. I just wanted to make sure you saw what it was. So we have n plus n squared over 2 plus n, right? What algebraically do we want to really do here to make this simpler? Now, number one, it's not okay to distribute the square root to each piece, right? That is totally, like, illegitimate algebra, right? You can't do that. You cannot simplify that numerator by distributing the square root on each piece. Yes? No, absolutely not. What else can't you do? You can't square it. you're not allowed to square it. Squaring it changes it. You can't do that, right? You can't square it. So, what can you do? You can rewrite it in such a way that it's equivalent to something else, right? That you can then use maybe a limit rule for. So it's the square root we don't like. Yeah? Now, your book does some other examples too where you're dividing stuff inside the square roots. You can also do that as long as you do it correctly, right? I think this is simpler. So, one thing I could do is say, well, okay, let's see. Maybe if I put the square root, right, over the whole thing, right, I would have n plus n squared on top. And then, what would I have in the bottom? Can I just like slap a square root and write 2 plus n? No. But can I write, good, 2 plus n quantity squared, right? This is positive, right? The square root of this, 2 plus n quantity squared is 2 plus n, yeah? And the square root of a quotient is the quotient of the square roots, yes? Okay, so this is a legitimate step. These two things are algebraically equivalent to each other, yeah? Now, we could treat this guy inside the same way we did the last problem, but it's just a square, so we might just instead multiply that out. Note, I don't want to take the square root because that would be going the opposite way. We just purposely didn't do that, right? We purposely created that. So let's do n plus n squared over 4, square out 2 plus n, right? Squared FOIL, right? That's what you got to do, yeah? So you guys tell me what I have. 4 is the F part of the FOIL, right? What about the O and the I? 2n plus 2n, good, 4n, and the L, n squared. Very nice. Yeah? So that's looking super nice, except for the stupid square root here in front, but we know that the square root function is continuous as long as its argument is positive, and therefore, what can we do with this limit? We have a limit rule that says we can take that limit right inside, right? That the limit of this square root is equal to the square root of the limit. Yeah? N plus n squared over 4 plus 4n plus n squared. Yeah? And now we have this limit inside here, which is a very similar limit to the ones that we've been doing for a while. And if I want to do this limit, it's infinity over infinity, right? I could either do it off to the side by myself with L'Hopital's rule and then come back. But what is our style? We've been dividing by the highest power of n in the denominator, right? Okay, so let's do that. So what do we get? Don't forget we have the square root, just stays on the outside, and then we're going to change our limit into, I'm going to divide everything in here by n squared. So it's n over n squared over n squared, 4 over n squared, 4n over n squared over n squared. Yeah? Okay, keep going. This is the limit as n goes to infinity. Whoops, the square root of the limit as n goes to infinity, right? What is n over n squared? 1 over n. The other guy is 1. Denominator, what do we have? 4 over n squared plus 4 over n plus 1. I'm guessing that you're getting pretty good at this and able to kind of start going from here to here. Okay? Alrighty, so let's see. As long as I see what you're doing, you're okay. Then where are we? Limit as n goes to infinity of 1 over n goes to 0. 4 over n squared goes to 0. 4 over n goes to 0. So what do we have? This is the square root of, what is the limit as n goes to infinity of my numerator? 0 plus 1, 1. Denominator, 0 plus 0 plus 1. Square root of 1, which is 1. What do I care about? In the limit comparison test, I care that it's not 0. If it's a finite number, I care that it's not 0. Because as long as it's not 0, I'm in the very first case of limit comparison test, and I'm golden. I can conclude that the series AN has the exact same behavior as the series BN, and my series BN was a divergent P series, so my series AN is also divergent. Okay, therefore the sum of AN diverges as well. Right? How did I know that BN diverges? I said it right here. Okay, you gotta say it somewhere. If you don't say it, I don't know you know it. Okay. It's up to you. If you don't say it up there, you can say it down here. Sum AN diverges since the sum of 1 over of 1 over n to the 1/2 is a divergent P series. P equals 1/2, which is less than 1. You gotta let me know you understand why. Okay? Okay. You ready to learn about the comparison test? Woo-hoo. So again, except for proving those two homework problems, you'll be pretty well set up to work on the problems in section 11.4. And then on Monday, we will look at proof ideas behind all of these guys, so you'll be better set up for proving those problems. Again, right now we're just stating all these tests. You don't know, maybe they're not true. Didn't show you any proof, so maybe I'm just making them up. You never know. All right, let's write down our last piece, the comparison test. Generally, abbreviated CT, okay? And it has the exact same beginning piece of hypothesis. We're going to let AN and BN be series with positive terms. Right? Okay. Which of those series that were up there in that corner from the very beginning, right? Which of those other tests required positive terms? Yeah, well, P series is positive terms. Integral test is positive terms. It came from P series, or in P series came from integral test. Integral test required positive terms, right? Remember? Yeah. Geometric series, divergence test, it's okay. You don't have to have positive terms, right? All right. So anyway, here we are. What does the comparison test say? Comparison test is two pieces, okay? The first piece says if the ANs are less than or equal to the BNs, okay? Now remember, this guy has, it's the same idea, unknown behavior, right? This guy has known behavior. You're kind of coming up with the known behavior guy. So if the ANs are less than or equal to the BNs for all n, right? Or at least for all n eventually, right? Doesn't matter if it's not true for the first several hundred even, but just if eventually, it's always, the ANs are always less than or equal to BNs. And what do you think is going to have to happen to the BN series in order to make any conclusion about the AN series? What do you think? Like, what is going to be the thing here? These guys are bigger. I want to be able to say something about this guy. Yeah, right? BN series has to converge, right? If I know the bigger guy converges, the comparison test says the smaller guy converges. Right? Makes sense, okay? And then, what's the other way. If my bn's are smaller than my an's, now you could write it the other way with an bigger than or equal to bn, right? But I still like thinking of it this way. It just makes more sense to me. This guy's our known, right? This guy's our unknown, right? So I have a known guy, and at least after some number n, all of these guys are smaller than these guys. Or equal to. And I know something about the bn series, the known guy. Then I'm going to be able to conclude something about the an series. What do you think it is? Good. Right? If the smaller things diverge, then adding up things that are bigger and positive, right, also diverge. Right? So don't forget, an's are positive, all of them, bn's are positive, in order to apply the limit comparison test or the comparison test. Okay? So let's jump into an example. Okay? Exercise 4. Here's our sum. N equals 2 to infinity of 1 over the square root of n minus 1. Okay? Okay. Notice we just started writing like sums. We don't even write where we start anymore, right? Because again, we don't really care what the sum is. We just want to, since it's hard to figure that out, we just care whether they converge or diverge, right? Here we start counting at n equals 2. Why do we have to start counting at n equals 2? Could we start counting at n equals 1 for this series? Good, no, right? If n is 1, denominator 0, then the first term blows up, right? That's not good. Okay, not in the domain, yeah? 1 is not in that domain. All right, so we start counting at 2 and life is good. The question is, does this guy converge or diverge? Sometimes the comparison test can just be a nice, quick, easy way to get to an answer, right? If it's an easy comparison to make. Otherwise, we're often using the comparison test to prove other tests, okay? So let's look at this thing. So we've got this guy square root of n minus 1 in our denominator, right? I need to set up some type of inequality, okay? So if I look at the square root of n, right, and I compare that with the square root of n minus 1, okay, then would you guys agree that the square root of n is always bigger than or equal to the square root of n minus 1? Yeah, right, we're taking 1 away from this guy, okay, yeah? So this is less than or equal to that, yeah? And these things are always positive because n is bigger than 2, right, okay? So if I divide this inequality, right, so this is a truth, I'm starting with this truth. If I divide this inequality, if I divide by the square root of n, right, then I'll get a square root of n in the denominator over here. But if I also divide by the square root of n minus 1, right, then I'll have a 1 up here, then I'll have a 1 there, and I'll have a square root of n minus 1. Right? Yes? Awesome. Very nice. Okay? So when you're doing comparison test, the way I want to see it done is I want it to be developed. Okay? So you came up with this inequality by some obvious starting inequality. Okay, so now tell me about this inequality. Well, this guy is a bn, right? That's the same as 1 over n to the 1/2. And we just talked about that guy not long ago. What does this series for 1 over n to the 1/2 do? It diverges, right? Right? P series, which is less than 1. So this guy diverges. He's smaller than him. Therefore, what can we say? That guy diverges. That's this piece, right? Here's our inequality. Here's our known bn, right? And here is our unknown an. and we just develop that inequality. Yeah? Okay? Another way to think about this inequality is that this, these two fractions have the same numerator, right? The same numerator, but this one has a denominator that is bigger than this one because this denominator is smaller than that one, right? A same numerator with a bigger denominator is smaller than something with the same numerator and a smaller denominator, right? Does that make sense? Did I just say that right? Okay. Same numerator, smaller denominator is a bigger fraction, right? Or same numerator, bigger denominator is a smaller fraction, right? Okay. That's also a reasonable justification. And that one was pretty fast, right? Okay. So, that might be a preferred method than setting up a limit comparison test. Yeah? Okay. But what if the problem was this guy? Doesn't matter, we can start at 2 still. What if we had that? Well, is there something super simple to compare with that, right? Well, if we try this process, right, well, we've got the square root of n is smaller than the square root of n plus 1, right? So if I do the fraction, then 1 over the square root of n plus 1 is smaller than 1 over the square root of n, yeah? And then what, right? I know that this guy diverges, but he's bigger, right? He's bigger than that, and so it's of no use. Does that make sense? This guy's smaller. This guy grows without bound, and that's smaller than something that grows without bound. You can't make any claim. Does that make sense? So a quick comparison test with 1 over square root of n isn't going to work with this problem, right? What would you want to do for that guy? Good. That would be a limit comparison test with 1 over the square root of n, right? Why? If I look at the limit as n goes to infinity of an over bn, I would have the limit as n goes to infinity of 1 over root n plus 1 over 1 over root n, yeah? Which is the limit as n goes to infinity, right, of root n over root n plus 1, yeah? Which is the limit as n goes to infinity of, just going to go straight there, divide everything by square root of n, right? 1 over 1 plus 1 over root n, yeah? Square root of n is highest power of n in the denominator, yeah? What do I got? This guy goes to 0. What do I left with? 1. 1 isn't 0. Therefore, the limit comparison test says that this sum does what? Good, diverges. Since this guy we compared with, this is our Bn, right? 1 over n to the 1/2, which is a divergent p-series, which we said 1,000 times today. Hopefully you will remember that. Diverges since 1 over the square root of n diverges. Yeah? If you keep writing down what the rule is, hopefully you won't forget it when it matters. Yeah? Okay. That is all for this week. It has been another fun week of Math 236 Home Edition. Look for emails and announcements from me. We will be diving into proofs of these results next week and then continuing with the next sections, maybe not in all the same order, with some more exciting new tests with different results, different things to be looking at the end to decide what the computation you just did tells you, right? So it's super important to get all of these things straight. Does that make sense? All right, I hope you have a great weekend. Again, it's just super sad that this is the way our semester will continue to play out, but hope to see you again next semester, not like this. Have a great weekend. Have some serious fun. Ha ha ha. Get it? Bye.